Trees in every country. Trees, you know we can work together and learn what we need to meet the challenge.
Hello, and welcome to the ISA Conference Rewind video podcast series. I'm Tanisha Price, instructional designer with the International Society of Arboriculture. Today, ISA is proud to bring you a presentation by Ryan Suttle and Nasko Apostolov about their study that explores how artificial intelligence can be used to predict tree risk. This talk was originally given at the 2021 ISA virtual conference, so the views seen here are those of the presenters. If you're fascinated by how technology can be used to enrich the study of arboriculture, you'll find something interesting here. Now, sit back and enjoy.
Right. Hello, everybody. Thank you for coming to our talk. My name is Ryan Suttle, certified arborist from the Department of Environmental Conservation at UMass Amherst.
And I'm Nasko Apostolov, a master's student in the Department of Civil and Environmental Engineering here at UMass as well.
And we're going to talk about the use of artificial intelligence for tree risk prediction today. So let's dive into it. Just give us a brief outline. So we have kind of the bones of our talk today. We'll start with an introduction into kind of the motivation for this study, as well as some broad use of artificial intelligence. And then I'll go over the data collection and description for what we used. And at that point, Nasko will take over and really get into kind of the nitty-gritty of the artificial intelligence side, talk about some of our results, which I think are pretty exciting. We'll get into some discussion and hopefully have time for questions at the end. All right, so to start us off, why study trees at all? I'm sure I'm preaching to the choir here today, but trees serve a lot of benefits in urban areas. They can decrease ambient temperature through evapotranspirative cooling, building energy use reduction, carbon sequestration, and storage, all three of which are only going to become more important as our climate changes. They remove air pollutants and can mitigate stormwater runoff and raise property values where they're planted less tangibly and quantifiably. They also have huge aesthetic and cultural value. Any of you watchers from Massachusetts may be familiar with this tree on the left. It's the buttonball tree in Sunderland. It's the largest tree in the state, and it's just gorgeous. It has tremendous aesthetic value and cultural value to that town. It's a historical landmark, and all of these benefits are maximized due to the size of the tree. However, with all these good things that trees do, there's also risk that they present, especially in proximity to overhead utility lines. A large portion of power outages are caused by tree failures. Trees kind of cause outages in two ways: falling into the lines and growing into them. Failures of individual trees coming down on the lines are by far the largest proportional cause of these outages. And mitigating it is a high direct cost to utility companies in terms of funding tree pruning and removal programs and infrastructure repair. Typically, utilities will spend millions of dollars annually, even small rural companies. And these outages also present a high indirect cost to the community, the customers that utilities serve. There was a really interesting study done a couple of years ago estimating $8.3 billion of lost revenue in a 10-year period in the state of Connecticut due to tree-caused outages alone. Between 2005 and 2015, so this was before we were doing everything online, I suspect that cost has gone up dramatically in the last couple of years. It could be an interesting future study. And all these things can lead to a negative perception of trees from the public and utility companies. So that kind of frames our research question for today. Can artificial intelligence be used to predict likelihood of tree failure and try to get out ahead of these outage events. There has been research into the efficacy of drive-by windshield surveys and walk-by surveys, and they're effective at identifying trees with an elevated likelihood of failure. So there's a potential for AI to process images to predict likelihood of failure in a similar way, which would promote efficiency as a potential to reduce costs, especially of large-scale tree risk assessment projects, and to increase data reliability through standardization of the process. So we took the approach to automate tree risk classification using a convolutional neural network. That's the type of artificial intelligence we use today. And Nasko will give us some more background on the specifics of that in a little bit. CNNs have been used in risk management before. Specifically, it's been applied to earthquakes and analyzing building structural health. However, its use in utility vegetation management is relatively new and complex. And that's because of the required degree of accuracy. As we all know, there's millions of trees along distribution rights of way throughout the country. And to assess each one, you need to be pretty accurate to mitigate that risk. There's also a lot of variation sources here in terms of different species appearance, seasonal trends, like deciduous trees losing their leaves in the winter, and growth habit. It has specifically been used in UVM for a couple of different applications, including estimating the distance to the conductor from a tree part, identifying density of tree stands along rights of way, and correlating higher density stands with increased levels of risk. But there remains a gap in deploying AI for predicting the use of, predicting the risk presented by individual trees. And as we brought up earlier, it's really these individual tree failures that are causing a lot of these outages. So it is a really interesting opportunity to see if AI can be effective here. So now I'll get into our data and description of that. I'm sure everybody has probably seen these two BMPs on the left here. So our data was collected in Eversource distribution rights of way across the state of Massachusetts, from all the way in the west and the Berkshires all the way out onto the Cape. So we had quite a few different study sites here, done at a level 1 risk assessment procedure. And it was a likelihood of failure assessment and a photograph. It was level 1 because photograph is by definition a limited visual inspection of the tree in question. So likelihood of failure, as we all know, it's 4 levels. So we had total of 665 images in this training data set, 459 of which were deemed improbable. 130 of them had a likelihood of failure of possible. 76 had a likelihood of failure of probable, and imminent was excluded from our model due to the rarity. I think we only had 2 trees that had an imminent likelihood of failure. And just to give us kind of an idea of what these trees looked like in the field, I have some representative photos here. So this tree on the left, this little leaf linden, there's no visible defects from this perspective. There's no dieback in the crown. So that was assessed at an improbable likelihood of failure. Similarly, this large London plane on the right has strong branch unions, no included bark. And this was also given an improbable likelihood of failure. Some possible trees here. This is a blue spruce. If you follow the trunk up about 3/4 of the way, there's a codominant union there. And there is some dieback in the extremities of the crown. So that union was given likelihood of failure if possible. And a similar situation here with the silver maple on the right. There's a low codominant union with some included bark. And there's also some dieback in the crown extremities. So this one was assessed as possible. And probable, this one is an easy identification here, just a stone dead sugar maple. And an American elm here. On the left, you can see above that crossarm, there's significant dead wood in the crown. All those leaves are actually ivy, so there's a potential for decay. And these were assessed as probable. And now Nasko will get into the methodology.
Thanks, Ryan. To give everyone an idea of the procedure that we used for developing our network, I'd like to share our framework with you all. So we used the raw images Ryan mentioned, 665 in total, and we performed some pre-processing procedures known as downsampling and horizontal flipping. So this data augmentation was performed in order to increase the size of our data set, which is a requirement for training our model. Once we obtained the pre-processed images, we created the classification scenarios where we combined different likelihood of failures, different categories together. So we had a total of 4 scenarios where the 3 likelihoods were either independent or grouped to, again, compare the performance of the model. And based on the different convolutional architectures that we had, we created some visualizations to see how what the performance was. And more importantly, we also tried, and this is part of our ongoing efforts here, to actually understand how the model learns and how those predictions are created. To give everyone an idea of what a convolutional neural network is, or CNN for short, it is actually based on the image recognition process of our own brains. So it essentially maps image data to an output variable. In our case, it's a class, the probable, possible, or improbable. So having these raw pre-processed images as input, we perform our pre-processing procedure, and then we perform the model training, which essentially is how the model learns to numerically map the image data to the image label that was given. And the final result is the image class prediction, which shows us whether the model correctly predicted an image which was given a certain label by an arborist. So our CNN implementation classifies these images accordingly. On the left here, you can see what sample raw input image looks like. Each image has a resolution of 4032 by 3024 pixels, which is quite large, and we had to actually downsample it for ideally enhanced model performance. So on the down right, you can see the downsampled version. What we also did in an effort to increase the size of the training set, we also performed the horizontal flipping. So from the total 665 images, we downsampled them to lower resolutions to speed up the computation process of the model. We used 3 resolution sets. And then we randomly selected 20%, which is equivalent to 133 images. Those were reserved purely for testing purposes. So the model is not biased during the training process, the stage of the training process. So the model is actually trained on 532 original input images. The horizontal flipping is essentially creates these mirror images, but it doubles the training set to over 1,000, which is really what we need in order to train our model. Now a little bit about the classification scenarios that we used. So there were 4 in total, and 3 of them were binary scenarios, where the first one was the probable improbable case, where we completely excluded the possible. So this wasn't a simplification of the original research question, but as you can see, this leaves out one of the categories. So we also decided to do some groupings. We grouped the 2 high-risk categories, the probable and possible, together. So they essentially constitute one class, and then we're training our model based on that, and the improbable class, which is left separate. Another scenario is grouping the possible and the improbable classes together, and then comparing it against the probable class. As you can see, this is just another one of the strategies that we have for comparing the performance and really seeing what optimizes our convolutional neural network. And finally, we have the 3 categories, all separate. So they're not grouped in any way. It's essentially a harder problem for the network to solve, since it has 3 outputs to label as opposed to just do in various forms. The goal of training our models is to maximize performance based on a specified metric and also minimize loss. This is not unique just to this problem, but to artificial intelligence in general. It's an optimization problem. So what our model and what we keep track of is the true positives, the correct predictions that belong to a certain class, the incorrect predictions, as well as the so essentially these are the true positives, false positives, false negatives, which are the incorrect predictions which do not belong to the particular class, as well as the true negatives. So the measure of performance that we chose was F1, the F1 score, which is a metric that keeps track of the sensitivity of those underlying factors, the true positives and the false positives, false negatives. And a score is in the 0-1 range, where a higher score indicates better performance and higher sensitivity. And to give you an idea of what the split is of our total number of images, we have the 1,064 images after performing data augmentation, and the 133 unique images unseen by the model previously before we actually test its predictive capability. Now we'll dive into the results and show you how our model performed overall. This graph tells us what the average F1 score is compared to across all 4 scenarios. We can see that the probable, possible, improbable case, where we group probable and possible together, performed best across the 4, and similarly the loss, which is the percent error of the model. So what percentage of the the classification is actually incorrect, and that's what it tracks. So the best one of the four scenarios was PRPO underscore IM, and it resulted in the highest overall F1 scores. We also included the confusion matrices, which specifically keep track of the probable, possible, and improbable predictions. So what essentially the way we read them is what was the true or the observed class as opposed to the predicted class by the model, and it tells us what is the highest percentage. So in the case of PRPOIM, on the top right, we can see that the probable possible class was correctly predicted in the highest form compared to the other three cases. One of the efforts, as mentioned previously, in answering this question was to actually interpret the results and not treat the convolutional neural network as a black box, but more of a interpretable tool. So there are many visualization techniques out there that let us study the learning process. What does the model deem relevant? What contributes to the final prediction? So in this plot, you can see the different visualization techniques that we are currently exploring. And the most relevant one in answering our research question is the GradCam, which stands for gradient weighted class activation mapping. It's the second one from the left. And it essentially creates an overlay on the original processed input, and it highlights the regions of the image which are most relevant for the final prediction. As you can see, this was a correctly predicted image with a probability of 100%, and it's a very relevant tool for the visual representation of the network's interpretability. This is an ongoing effort, so we continue to make progress on this.
Yeah, I would like to just kind of point out one thing on this GradCam image here, is that there is a limb on the right-hand side with a very sharp bend, which can be a stress razor and a weak point under a significant load. And this GradCam is picking up that area. So it's looking like it's assessing the tree in a similar way to I was in the field, which was really, really exciting to see. So I'll take over the discussion here, just some kind of summary points, some key takeaways, as well as mentioning some future work that we hope to do. And then at the end, hopefully we'll have some time for questions. So in summary, this pilot study demonstrates that AI can be effectively used to automate tree risk assessment, at least in likelihood of failure, from photographs. It was able to correctly predict the field assessed likelihood of failure with a high degree of accuracy. And again, this, in future stages has the potential to decrease budget demands of large risk assessment projects by highlighting these higher or more probable likelihood of failure trees and potentially identifying them for more detailed assessment. Now, one limitation is a variability among assessors, especially between the probable and possible categories of likelihood of failure. There have been previous studies done showing that improbable and imminent trees, most arborists can agree on what those look like. The possible and probable, the two intermediary categories, are kind of where professional judgment comes in and experience. So delineating between those two classes is a limitation that running more images through this CNN would help address. In future work, validation with multiple arborists to try to address that variability among accessors would be an awesome next step here, as well as quantifying the interpretability of the network's classification process, like Nasko described, trying to unpack that black box and see how this CNN is reaching its decisions to see, are the areas of interest the same as what the field assessor is seeing in the tree. And finally, we'd just like to thank everyone who made the study possible, including Eversource Energy, Networks for Accessibility, Resilience, and Sustainability Laboratory, and the Department of Civil Environmental Engineering, and the Department of Environmental Conservation at UMass Amherst. Thank you.
Thank you.
Traditional skills and modern techniques. Whatever language you speak, you have a world to offer every day. Climb with the ISA.